Hello, everyone, and thanks for joining this part of Kubeflow Dojo series, which we are running, where we are essentially going through the end-to-end machine learning lifecycle using Kubeflow. And each of these different series, we are diving into different components of Kubeflow. As you are aware, Kubeflow is an end-to-end machine learning platform on Kubernetes built around constructs of build, train, deploy, and manage. For build side, we have Kubeflow notebooks, which is there at how to run notebooks on top of Kubernetes. Then we have the distributed training and hyperparameter optimization. So for distributed training, there are operators like TensorFlow, PyTorch, XGBoost, MPI. And for hyperparameter optimization and neural architecture search, there is a component called CATIM within Kubeflow. Specifically, when we talk about model serving side, there is Kubeflow serving as well as Seldon comes pre-integrated with Kubeflow. So in this talk, we are going to dive deeper into aspects of model serving, leveraging Kubeflow and specifically KFServing. And tying all this lifecycle together is Kubeflow pipelines, and we have another Dojo deep dive into that particular component if you're interested there. One of the questions we often get is, why is production model serving so hard, right? We have been deploying applications in production for, a couple of decades now. And is there something which is fundamentally different in the machine learning and AI world, which essentially makes this, very hard? Now, there are various factors to consider. I think one of the key things, which is, more peculiar to machine learning and AI world, is that it's very, very experimental in nature, right? So the traditional life cycle where you have applications probably rolling out once in 3 months, once in 6 months, right? The next version. That doesn't technically apply because there is constant change happening. Your data set is changing. Your model once deployed, it's drifting. There are anomalies. There is other factors to consider. For that, you may need to go back, retrain, because you got new data or your model was not showing the predictions it should be showing. So you have to iterate over it multiple times. Now, when you are deploying and rolling out new versions of these models, you want to consider questions like, is this rollout safe? How do I roll back? Can I test a change without swapping traffic? Right. So a lot of those things come into place, right? Now, another thing is that, you have models of multiple types. You have TensorFlow, XGBoost, scikit-learn, PyTorch. How do you provision them and deploy them in a consistent manner? And then you monitor them as well, right? Now, after deploying, another thing which you want to consider is that you want to be able to have a standardized data plane protocol to be able to call those models for prediction, for explainability, right? So you're not actually writing a client in multiple ways based on the model which is deployed, right? You want to standardize around that data plane. Then, you also want to ensure, there are monitoring capabilities, right? So how can you explain the model predictions, right? Are you able to detect outliers and skew? Are you able to do bias detection? Are you able to do adversarial detection? Another thing, right, which comes into picture is more often than not, what your model expects as an input is not what your end user is giving, right? So you essentially need to be able to plug in custom components for pre-processing, post-processing, right? So what you're sending to the model is modified, and then the response you're getting from the model is also, you're massaging it before serving it back to the end user. Right. So I think if you look at the challenges, right, in this world, right, they are enormous. And what was happening was, when close to around, I would say, a year and a half ago, there were different teams doing different work in this area. Certain Core, has been around for much longer, very strong open source project in this area. And they were pioneering, a lot of the constructs around graph inferencing. IBM and Bloomberg, right, we were exploring a lot of the serverless ML lambdas. Tommy, who is here, who gave it, and myself, we gave a talk into KubeCon. And by the way, we didn't introduce ourselves, right? So maybe I will just take an opportunity here as well. So my name is, Animesh Singh. I'm the chief architecture in the data and AI platform open source strategy team here, and I'm leading IBM's engagement with Kubeflow. Tommy, do you want to go very quickly?
Hi, my name is Tommy, and I'm one of the software developer in the IBM open source team, and I work on the Kubeflow project across many different components.
Yes, and Tommy has been contributing, tremendously across, the whole parts of Kubeflow lifecycle, whether it's serving, pipelines, training, hyperparameter optimization, or the Kubeflow control plane. Okay, so one of the things which we did, which was in KubeCon, I would say December 2018, right? Tommy and I presented on, using serverless Knative way of serving models, right? And that talk became, very popular. We got a lot of requests, and then that also, laid out some genesis around, the origin of KFServing. Now, Google, as we all know, has been, doing great work around, serving TensorFlow models using TF-serving, which is, production level model serving platform for TF-serving for TensorFlow models. And then Microsoft has been, focused heavily on moving the Azure machine learning stack on top of Kubernetes. So a lot of those doing different things, but around a common problem. And somewhere, around the first quarter of last year, right, we decided to come together and start forming this agenda for launching, Kubeflow serving so that we can target, a common set of requirements and build an industry standard model serving platform to handle 80% of the use cases which come in the model serving world. Right, so essentially founded by Google, Sheldon, IBM, Bloomberg, and Microsoft. It's part of the Qflow project, and the initial focus definitely has been in handling the 80% of the use cases, right, which come as part of it. So, do single model rollouts and updates. And the goal is, essentially handle and incorporate the serverless characteristics. So scale to 0 when there is no traffic, which you can optionally configure to scale to 1 if you don't want to scale to 0. Having the capabilities around canary rollouts, model explanations, pre-processing, post-processing, and we will talk a bit more detail as we go through this. This is at a high level what our stack looks like, right? At the very bottom layer, definitely there is Kubernetes, which is interacting with your hardware and compute infrastructure, leveraging the GPUs and the TPUs and the CPUs under the covers. And then we bring Knative and Istio on top of it to give us a lot of the capabilities which we need around the serverless characteristics or canary rollouts, etc. And then a lot of the capabilities built into KFServing to standardized model serving for all these different frameworks, whether it's TensorFlow, PyTorch, Scikit-learn, XGBoost, enable auto scaling, scale to 0, and then give a standardized interface for model prediction, pre-processing, post-processing, explainability, and moving forward in other areas around model management. So I mentioned Knative, right? And very quickly, one of the things which we want to highlight is the part of Knative which we are using is Knative serving within this project. And IBM is the second largest contributor into the Knative ecosystem. And this is a project which has become very popular into the serverless arena, and in it being used to, handle a lot of the open source projects which are coming around, which need, serverless capabilities. We leverage Istio, and what Istio brings to the table, again, this is a project which was founded by Google, IBM, and Lyft. IBM is the second largest contributor here, and what it brings to the table is, the notions of connectivity, observability, security, and control. The area which is most important out of this for us is definitely, the traffic control, load balancing, right? Because we leverage it heavily for our canary rollouts and other capabilities which we provide. And definitely, the observability infrastructure which comes as part of the Knative and Istio around metrics, logging, and tracing, tremendously help in terms of surfacing some of the metrics which we need to see. So what do we mean by canary configuration, right? So essentially the idea that, you have a version of the model and then you want to roll out a new version of the model, right? And while rolling out, what you want to ensure is that instead of diverting the whole of traffic to the new version of the model, you want to take a very selective approach, probably start from, a percentage, then increase it based on the model performance, right? So this is what, canary capability gives to you. Now, One place where it differs a bit from the Knative constructs is that you can have multiple revisions within both the default as well as canary configuration. And again, one of the reasons for us, doing this was to enable, more GitOps paradigms. But again, the core thing which plays into this is that ML world is very experimental. Even when you have a version of the canary, you probably are, producing multiple revisions of it before you are satisfied this is your canary, right? So this enables you to work at a granularity, right? That you can have even multiple revisions from a canary perspective or from a default perspective. Different kind of model serving frameworks are supported, right? So we support TensorFlow via KFServing. Then we also support, NVIDIA's TensorRT, now called Triton server, which is essentially optimized heavily to work with GPUs, and you can essentially serve a lot of these models using the covers. For PyTorch, you can use the custom framework which Kubeflow serving or KFServing provides GPUs, or you can leverage something like Onyx runtime, which also comes bundled with KFServing to convert your models to Onyx format and then serve it using that, right? And then we also have custom model servers for XGBoost and Scikit-learn. We support multiple types of storage, S3 compatible storage, Google Cloud Storage, Azure Blob, persistent volume claims. So, regardless of the storage flavor you have, KFServing should be able to work with it. And as I talked, right, there has been a lot of focus around pluggable components, right? So predictor, which is essentially the heart of your model serving, but then, things like transformer, which allows you to plug in preprocessor or a post-processor explainer. And a couple of things which I don't have it on this chart is something like, logger, which allows you to then, enable payload logging, and I will talk a bit about it as well. When you look at the logical architecture, right, this is how it looks like. Your request comes in for prediction or explainability, right, or as more capabilities get ingrained. And essentially, the transformer then after, the initial routing happens, right, whether you are going to the default or the canary, from there onwards, right, transformer can decide, whether it has a role to play in terms of routing a request for pre-processing and getting the pre-processing done before calling the predictor, or call the predictor directly. Typically also, looking at the spec where there is an explainer needed and we need to call the explainer, right? So that's the role being played there. Now, when you actually look at how it translates to the underlying infrastructure when these things are deployed, right? When your external traffic is coming in, there is STO ingress gateway with the Envoy proxy, which is the default, right? Which essentially handles, the routing of the traffic. Then there is the activator, right, which comes as part of the Knative serving, which is essentially responsible for your auto scaling capabilities, right? So based on your request based on your QPS, you can have request based auto scaling, and also depends on the concurrency targets your particular model server can handle, right? And that's also the component data back into the Prometheus for metrics, etc. And then, the other components of Kubeflow or serving or KFServing essentially translate to different pods, explainer, predictor. If you have a preprocessor or a post-processor, all these, translates to different pods on the underlying infrastructure. Now, one of the things which I did also mention was that, beyond the specs which standardized how you deploy these, focus was essentially data plane standardization. So if you have written applications or clients which are calling these models and getting your predictions and embedding it on your client-side code, if the data plane is standardized, you don't need to be, change it if you're moving your models across multiple of these frameworks, or for example, you're moving your models across, different cloud providers, right? So that's one of the efforts which we are driving in this community as well. Right, and the V1 data protocol, which is already part of KFServing, that gives you a TF-serving compatible HTTP API, right? And then we are looking at gRPC based implementations as well, But the focus now, from the compatibility perspective is shifted to what we call V2. So what you see here is, the V1 protocols around explainability prediction, checking the readiness of the models or getting the list of the models. With data plane V2 protocol, we are even going much deeper into that. And, I will be able to point, if you have time in the end, right, towards the GitHub repository, which explains, all the standardized protocol which has been created around V2 for prediction, explainability, getting whether the not. Um, and at this point, NVIDIA's Triton server has already implemented the V2 protocol. Selden is implementing the V2 protocol. And then, there are efforts, right, in terms of having the Onyx runtime or KFServing also, follow the V2 protocol, which has been standardized and put forward in the KFServing community. Now, when you look at the specs for deploying, very simple. In this case, like if you look at like 8 lines of YAML, which is consistent across whether you are deploying scikit-learn, TensorFlow, PyTorch model. Typically, where is your model, right? And what name you want to give it, what's the kind of it, and then just, push it on. Now, then you can expand on those 8 lines, right, and add more lines, right? So for example, in this case, we are saying we also need a canary instead of, just a default, right? So then, okay, where is your canary model line and how much percentage of traffic do you want to route to it? Pretty simple, pretty straightforward to understand. And then, that's enabled. Now, as I mentioned, right, for TensorFlow serving, we are using for TF serving, which comes, from the TensorFlow umbrella, right? It's very stable. Google has been using it internally as well since 2016. It supports both the saved model format as well as the GraphDev format, written in C++, and supports both REST and gRPC. Now, what KFServing brings on top is, an ability to spin off an inference service with KFServing very quickly, scale back to 0, provide auto scaling with request-based auto scaling characteristics, and then, enable that KFServing to leverage, the underlying GPU capabilities within the context of a Kubernetes environment. Now, if you look at this particular, deployment, this is essentially using a BERT model, using, KFServing in this case, then specifying I need, 1 GPU for this particular model. And then I also have, a transformer, which is handling the pre-processing and the post-processing, right, which is essentially tokenizing a lot of the inputs before getting passed, right, to the predictor. We support NVIDIA's Triton inference service. It's very highly optimized model runtime for GPUs. A lot of folks, consume models which are deployed on GPUs, given that, model inferencing requires very compute-heavy infrastructure under the covers, right? And apart from supporting that, right, Triton also supports, model repository, versioning, dynamic batching, concurrent model execution. And then, you can actually deploy your TensorFlow, PyTorch, Onyx models using TensorRT. And if you are using specifically BERT-based models, right, TensorRT Optimizer can further bring down that inference latency. Again, very simple to use from the perspective of KFServing, exactly the same YAML, right? You don't need to change the pre-processing and post-processing function at all, but you just need to point to be able to, what is the predictor you are using, in this case TensorRT, and what is the version of that predictor. That's pretty much the change. And instead of using KFServing, you can point to Triton inference service. For PyTorch model server, we have our own implementation within KFServing, right? It's implemented in Python with Tornado server, right? And using the model state dictionary for PyTorch saved models. That's what is leveraged currently, which is also, the most recommended method in the PyTorch community. And we have also enabled, GPU inferencing using that from KFServing 0.3 release. Now, as I mentioned, you can alternatively convert it to Onyx format, run it using Onyx runtime. And another aspect which, we are working on is having, AWS contribute the Torch server runtime, which has been released in KFServing as well. Onyx, definitely, something which has become very popular on the model standardization side, right? It's a performance-focused inference engine for Onyx-based models. So train using any of these popular frameworks, TensorFlow, PyTorch, XGBoost, scikit-learn, but then, convert to Onyx and serve it using Onyx, right? So that's the promise around it. Again, written in C++, supports both REST and gRPC, right? And you can again use Onyx to further optimize BERT-based models, right? Which is something if you're using heavily in your infrastructure. Now, again, I mean, same spec, right? And the only change you are doing is you are saying that use the PyTorch predictor, and that's pretty much right. And what is the runtime version for that PyTorch predictor? Or when you are using Onyx, you're pointing to the Onyx runtime. Okay, so now that you have seen, how simpler and how easy it is to switch between different runtimes, when you're deploying your models, right? Um, how do we actually enable auto scaling? So as I mentioned, right, we use knative autoscaler, which allows you to scale to 0 and scale up from 0, right? And you can use, based on both request-based auto scaling, so number of in-flight requests, you can define a concurrency target. For example, if your model server can handle 5 concurrent requests, then in that case, this should be able to spawn. And if you're sending 50 requests, KFServing should be able to spawn 10 instances of your model server to handle those 50 requests. Right. So I think summarizing, the deployment part of KFServing, right, the areas which we want to highlight are that, running on top of Kubernetes and Knative, leveraging the best of the breed cloud native infrastructure, best of the breed integration with GPUs, right? And using auto scaling based on request based queues. So then, you're not constrained by, the limitations and the gotchas which come because, you are doing auto scaling based on GPU or CPU utilization, which still remains buggy to a large extent, right? And then, you can leverage, the underlying gRPC protocol from a lot of these model serving platforms. Okay, so that covers, the I would say the serving part of the production model deployments. But beyond serving, right, once you have deployed your model, what happens? You need to monitor them, right? So, and the kind of things which you need to monitor them for are like there are concept drifts. Is the model vulnerable to adversarial attacks? Is there an outlier? Can the model explain its predictions? Right. And typically, if you look at, production machine learning architecture, what you would want to do is, as your requests are coming, right, to Kubeflow serving, you would probably want to have something what we call here is a logger component, right, which essentially can do a logging of request and response. And then from there onwards, you can push that to a target of your choice. Now, that target can be a queuing system, it can be a relational database, it can be an object storage system, right? But from there onwards, right, you can do more things, right? So then you can enable things like outlier detection. You can optionally configure alerting based on top of that. You can enable adversarial detection. You can enable concept drift. All these capabilities, you can enable once you are able to log your request and response, right? Because they traditionally need more than just a single request response to be able to do these analysis, right? You probably want a little bit of history, how your model is performing over a period of time to be able to give these predictions or, these analysis. So payload logging, right? As I mentioned, captures payloads for analysis and future retraining of the model. And it's mostly asynchronous and offline, right? So the logger component essentially works, and it doesn't come into your main prediction path. It gets triggered and it's doing its job in parallel. You can add it to any inference service endpoint, right? Depending on what you want to log, right? Typically, it's a prediction, right? But if you want to log the explanations as well, right? Because there are a lot of explainability algorithms which need the traditional explanations to create, more intelligent explainability based surrogate models, right? So you can log request responses or both. And then, you can simply specify a URL to send these payloads. So this we have implemented using cloud events, which is, standardization effort into the CNCF community to standardize how events are defined and sent. Right. So typically in this case, if you look at the spec, if you are introducing logger, you need to provide, in which context. So in this context, the logger is standing in the context of a predictor. This is a URL where to send the logs, and that's pretty much what you need to do. Very simple, very straightforward. Right. And again, as I mentioned, this gives you capability to leverage different kind of endpoints, right? So somebody can send it to Kafka in this case, right? And you can use Kafka cluster, for example, to store these logs. Okay, so that, how do you capture payload logs? Now take a look at learning explanations. Now, why is this particular field very important is because more and more, your models are making real world decisions. Right. So whether you're getting admission to a university, whether you are getting admitted to a healthcare system, whether um, you are essentially your resume is getting routed to the hiring manager, right? So these models are making, very, very important decisions, and in some cases, life-altering decisions. Like, for example, what should be your criminal sentence, right, for your offense? And for these, models which cannot explain what they are doing and how they are doing and why they arrived at a particular prediction, both in the context of that individual prediction, but also over a period of time. Most of the institutions wouldn't put them in production, right? So that's where, explainability becomes very important. So in this case, again, you can, add explainer as one of the components by just injecting what type of explainer you want. By default, currently it comes with certain alibi explainer, right? And then you can point to the storage URI for that. This is the Seldon team, right, which is behind the alibi explain, and they provide state-of-the-art implementations around anchors, counterfactuals, contrastive explanation, which is an algorithm which was contributed by IBM Research into open source and is being used as part of the alibi explainability as well. Now, excuse me. Within this space, we have our own project, right? IBM has a project in this space called AI Explainability 360, which we recently donated to Linux Foundation AI. So now it's a neutral and open governance model, and we will be seeing soon rollouts around that. And AI Explainability 360 is a toolkit, right, which actually looks at explainability from the whole end-to-end lifecycle perspective. So you can use this toolkit to explain not only explain models, but also the data sets, the samples and the features in a data set. You can do local explanations for individual model predictions and transactions, but you can also do global explanations around what this whole model is, how has it been explaining over a period of time, and then you can have a surrogate model which runs on this side. So a lot of these algorithms are still established there as well, and you can get more details about this from the website which is listed there, but it's also in GitHub as the link which you see there. Now, again, when you look at, from this perspective, how will you enable it within the context of KFServing, right? So you see there is an explainer as a component, right, within your spec, and then you say, okay, which is the image for that explainer. Now, you can also define, type for that particular explainer, right? So in this case, one of the things with AI Explainability 360 is it also provides, algorithms from Lime or SHAP, which are very popular open source tools for explanation, right? So in this case, you can explain images using the Lime algorithm, and then you also want to, if you want to establish some of the defaults for the capacity, right, which your explainer should use. And some of the more advanced capabilities, right, which are ingrained in KFServing around outlier detection, adversarial detection, concept drift, and depending on how we are doing with time, I may probably skip a bit quickly through these, right? So again, with outlier detection, right, the key policy is that you don't want to trust prediction on instances which are essentially outside of your training distribution, right? So there are different capabilities, right, which has been contributed by Seldon, different detector types, like whether you are doing stateful online versus pre-trained offline, which can detect then, outliers based on, model predictions. Excuse me. So the next is adversarial detection. Now, one of the things which again is happening quite often is that, your inputs can be adversarially manipulated, right? And in a lot of cases, the adversarial noise which is generated in these inputs can be undetectable to human eye, but when essentially it's sent to a model, right, the model gives totally different prediction, right? So in this case, for example, if you see, an image of a pig being changed, which is, adversarially impacted, there is no visual impact for a human eye to see, but, the model predicts airliner. Now, similar think in the context of, the images which are on the left-hand side, right? If 0 is adversarially impacted to a certain degree, the prediction of the model is 2. And when you look at 6, if it is adversarially impacted, the model comes back with a prediction of 0, right? So very important field. A lot is happening in this area as well, right? And then, the concepts around, concept drift, which has been also, contributed by Selden within this. And, it works on the same principles around, which we talked about previously, right? And you want to make sure that, your production data distribution is not essentially, exactly the same as training distribution in that sense. And then, you're able to detect, concept drifts out of that. Now, when you look at it from that perspective, right, typically in this case, for a CFAR 10 model, right, you can essentially use the same architecture, which is the architecture with the logger, right? And you can bring outlier detector at that particular point in time, after you are able to collect a bunch of input and output responses, and then leverage that to actually detect, outliers for your model predictions. And the same concept, which you can use with, adversarial detection, right? As I mentioned, there is a default integration with Alibi Detect, which allows you to leverage these capabilities. And we have also, created a prototype which we are going to move out into KFServing soon, which is essentially, how to leverage another toolkit which we have in IBM portfolio, but donated to Linux Foundation AI, and in the process of getting incorporated there, which is called Adversarial Robustness 360. A very popular toolkit in this space, works around a collection of machine learning and deep learning models, multiple algorithms to actually detect, adversarial attacks. Then gives you mitigation algorithms. It also gives you metrics how to essentially assign scores, whether these input predictions are or can be adversarially modified, and works across both deep learning as well as machine learning models. One of the things which this chart doesn't capture is like beyond TensorFlow, Keras, PyTorch, it now has support for machine learning models like scikit-learn, XGBoost, and others. And it also works across the spectrum of image as well as text, tabular data as well. So this sort of gives you, a resource list of the different GitHub repositories you should be looking at. So essentially, KFServing and Selden Core, right? If you're interested in a lot of these cases. But, individually, if you want to look at the explainability, right, from Selden Alibi or IBM AI Explainability 360, you can go there. If you are essentially looking for, outlier and adversarial detection, there are samples within the KFServing repository as well. But if you want to look deeper into the code, you can go to that particular repository. And then obviously around, adversarial detection, from IBM's perspective, you can look at the github.com/IBM URL, which is listed at the bottom. So with that, I will pass on to Tommy to actually, walk you through some of these capabilities and show you in real life, how it works. Tommy, you are on mute, I believe. Yeah.
Thanks, Anish. So I'm going to show you the demo for KFServing. So for today's Dojo demos, you could find it under the IBM Kubeflow Dojo, under demo material, day 2 KFS. And this is the notebook we were going to showcase today. And once you get this notebook cloned, you could go ahead and access the Kubeflow main dashboard click on the notebook server and create a server to run this notebook on the Kubeflow cluster. So once you have the server running, then click on connect. This will let you log into the Kubeflow server to run Jupyter Notebook. And today we're going to run the KFS demo notebook here. So first, we are going to introduce how you could run KFServing using the KFServing SDK on Python. So before we run this, we need to install a list of dependencies. So we go ahead and run a pip install on the KFServing SDK. And while we're waiting for that, we are going to assign the IP for this cluster, so it knows where to ping the traffics. So once we assign the IPs, we're going to execute the prereq for this notebook. And now we're going to try our first example with TensorFlow. This example is using the TF-flower dataset. The dataset is containing a set of images and predict one of the 5 flower classes listed over here. So to run these examples, we first did initialize the KFServing SDK. We import it into the Python kernels. Then we need to get the namespace we're using right now, which is anonymous. And then here we define the spec for the KFServing using the SDK syntax. And here we're using the V1 Alpha 2 APIs for the predictors. And the models is pulling from the GCS storage. And we assign the CPU to 0.1 virtual CPUs and 1 gig of memory. And once we're finished, then we assign the name of the models, which we call flower samples. And once we have ready, we declare the KFServing clients and create these services. Once it's created, you're just able to see the metadata returned from the Kubernetes API. And you could also use the KFServing get to get more detailed status. So right now, the model is still waiting to be served. So it will have false for the ready status. And after like 20 to 30 seconds, it should show the ready status to true and let you know what is the endpoint you're supposed to use in this case. And while we're waiting for that, let's explain what we're going to predict using our predictors. So in today's example, we're going to use this image for the flowers. And we'll take like the raw image and encode it in base 64 and send it directly to the models above. So once the model is ready, then it will show you like what URL you're supposed to use. And since we already defined it in our prerequisites, so we could just directly use the model influencing helper functions and do the predictions. And once the prediction returns, you're just able to see a list of results. So since I think it's the first time, so the model still needs a little bit of time in initializing. And once it initializes, you're just able to see the confidence score is the highest for the first class, which is the dandelions. So the prediction is correct in this case. So now let's go ahead and try a different way to deploy KFServing. This time let's first clean up the previous examples. And this time we're going to use the KFServing pipeline to deploy our KFServing models. So in order to run the pipeline, we first need to declare the clients for the Kubeflow pipelines in Python. So we want this block of code to declare the clients and create experiments for the KFServing. And once we have that, we're going to define like what operation we're going to use, which we will put directly from the preset components on Kubeflow pipelines, and create a pipeline definition for these components. So in this definition, we're going to use a default models, which is the same as above, and we also create a canary models with a different model source. So in this case, the canary models, we're going to get 10% of the traffic. those will get the remaining 90% for the A/B testing. And then we also have other parameter that's for the namespace on anonymous, and we were serving using the TensorFlow frameworks. And once we map all the parameters to the operations, then we could run the compilers to compile the pipelines into a executable source code. Then we will run that source code with the TF-flower name for this pipeline. So let's execute it, and you will be able to see a link to the GitHub pipelines dashboard. So since it will run it inside in separate containers, so it will first need to instantiate a new container to run this executions. And the execution is very similar to what we had before. So we were able to see the status of the model name and whether or not it's ready to be served. So it's the same as above case. It probably takes 20 to 30 seconds for both of the models, the canary and the default, to be served on this cluster. So let's wait for it. And once it finishes, you will see the URL for predicting these models. So once it's ready, then let's try it out again using the same inference helper functions. And we could see that there's the same results on that particular flower image. And since it's a canary models, we want to see how the traffic gets split into 90 to 10. So in order to do that, we will run a infinite loop to generate traffic to these models. And once we generate the traffic, we could use one of the monitoring dashboard called Kiali that comes from the HDO deployment. And here you can see right now we just started to generate the traffic. So most of the traffic is going to the default predictors. And the rest of the traffic is around 10% going to the TF-flower canary predictors over here. And that is the end of the canary examples. So now let's go ahead and stop this and go into some more advanced example using the transformer. So the transformer is basically you can add a certain container to do the pre-processing and post-processing before the actual prediction happens. So in this case, we would be using the CFAR10 datasets on a PyTorch server and using a transformer to pre-process the image into like 32 times 32 pixel with 3 color channels. And here is the set of sample CFAR10 datasets. It has 10 different classes. And see, you could check the example link and see what the preprocessor function looks like. So the preprocessor function is basically just take a raw image in base64, parse the bytes, and then do a normalizations and convert it into like the 3-dimensional metrics. And once it's converted, then it will send the converted metric to the back to the predictor host, and then in the back. And for the post processing, it was just returning a raw tensor back as a result, because there's nothing need to be post processing in this case. So since this model was going to take a while, so I already pre-executed. And to define these models, we could simply use YAML format with it. So we can see the models could be pulled from Google Cloud Storage. And then we could define our own images for the transformer to do pre-processing and post-processing. And once the YAML is applied, then there should be two different two different parts that get provisions. One is for the actual model prediction, and one is for the pre-processing and post-processing. and they both share the same endpoint. And once the inferencing happens, so in this case, we're using a cat image with 32 times 32 pixels and encoded with base 64. And we could see the fourth class, it has the highest confidence score. And once we compare to the class labels, which is a cat and is correct in this case. And we could also use the same method to generate traffics. So in this case, I will show you videos of the previous example I have executed. So once you generate traffic for these examples, you're able to see the KILI dashboard similar to this. You're able to see most of the traffics. I mean, about half to half of the traffic are split to transformer and predictor, because each transformer prediction also need to call one request to the predictor to get the results. And you could see the predictor prediction is actually triggered by the transformer parts in this case. And now that is the end of the transformer examples. And another plugin we could add is the explainer. So in this case, we're going to show you how to add an AIX 360 explainer to KFServing. So as we mentioned before, AIX 360 is a library we developed in IBM that do model explanations. And you could see more details under github.com/IBM/AIX360. And in this case, we're going to define very similar as the above examples, where we have a models serve. And this model we're using for AIX360 is the MNIST, the handwritten datasets. And for the explainer, we're using a container with the Lime image predictor types. So we're technically using the Lime libraries to get every predictions explained in a black box fashion. And this is the high level views of how this is going to be done. So all the traffic is technically going to the AIX explainer first. And the AIX explainer, once it receives the traffic, it will first using the still local gateway to get to the predictor and give the model results back. And once it get back the first model samples from the predictors, then it will generate few more sample predictions to figure out why this prediction has this amount of confidence score. And once everything is calculated, then it will return the actual explaining outcomes back to the client. So to create the AIX example is very simple. It's the same thing to create the YAML files and apply it to the cluster. It will have the same behavior where it has the part for the explainer and the part for the predictor. They both share the same endpoints. And over here, we're doing a simple prediction, but we have some extra post-processing code to actually visualize how the images looks like and how they get explained. So the image we're going to send is a number 2 pixel image. And once you send the image to there, it will return a result. And then they explain that list of confidence score with why is having that confidence score for each class. So in this case, the red dot is the confidence is the pixel feature where it says it's positive for that confidence score. So you can see both of the number 2 pixel are returned positive. And also for the class A and class 4, they are also pretty high because there's a lot of the pixel saying positive for those class as well. But for number 9, number 5, number 3, number 6, there's almost no pixels saying this class is positive. So we can see why this model is returned 2 in this case. And that's the end of the demo. Thank you very much.
Thanks, Tommy. That was great. I think you covered very well the different capabilities, right, which are present in KFServing. So I think again, thanks everyone for joining. Right, these are the GitHub links, right, which should look at, right? And if you're looking for, where the Dojo is currently hosted, it's github.com/ibm/qflowdojo. And thanks again. If you have any questions, do reach out to us through issues on any of these GitHub repositories or through the Slack channels. Qflow's Slack workspace has a Slack channel dedicated to KFServing. We also have, Slack channels specific to toolkits like 360 or Adversarial Robustness 360. Once you go to those GitHub repositories, you can, see the information how to join those Slack channels. Thanks again. Thanks for joining. Thanks, Tommy.
Thank you.